Engineers at SpaceX built an engine so powerful, so precise, and so dangerously complex that if a single valve opens half a millisecond too late, the whole thing explodes. Not malfunctions, not stalls, explodes. And yet, they keep building it, keep testing it, keep pushing it harder than any rocket engine in human history. This is the Raptor engine, and it may be the most important and most terrifying machine ever assembled. To understand why the Raptor is extraordinary, you first have to meet its predecessor. The Merlin engine, Falcon 9. You've seen the launch's 18 engines firing in perfect unison, a booster gliding back down and landing itself on a drone ship in the middle of the ocean. The Merlin made all of that possible, and it did it through one very deliberate design philosophy. Keep it simple. The Merlin burns two things: liquid oxygen and kerosene, basically a refined version of jet fuel. It's proven technology, predictable, cheap. And when SpaceX was a scrappy startup burning through cash in the mid-2000s, cheap was the only option they had. Its thermodynamic cycle, the way it manages fuel and pressure, is called an open cycle. Some of the exhaust generated by its turbines just gets dumped overboard. Wasted, vented out. Inefficient? Yes. But forgiving, controllable, safe enough to iterate on fast. The Merlin kept SpaceX alive. It took astronauts to the ISS. It launched satellites, scientific instruments, GPS networks. But it was never designed for Mars. And when Elon Musk stood in front of a crowd in 2016 and announced SpaceX was building a rocket capable of colonizing another planet, the Merlin, great as it was, simply couldn't do the job. They needed something different, something radical. They needed the Raptor. The first decision SpaceX made with the Raptor was the fuel, and it's one that raised eyebrows. They chose liquid methane. Rocket engineers had used kerosene for decades. It's energy-dense, easy to store, and well understood. But kerosene has a problem. It leaves a residue. Carbon deposits, soot, build up inside the engine after every burn. For a rocket you throw away, that's fine. For a rocket you're trying to launch hundreds of times, it's a nightmare. Methane burns cleaner, far cleaner. That means less buildup, less maintenance, faster turnaround between flights. For SpaceX's goal of radical reusability, landing Starship, refueling it, and launching it again days later, methane was the obvious choice. There's also a longer game being played here. Methane can potentially be produced on Mars using carbon dioxide from the Martian atmosphere and hydrogen from ice through a process called the Sabatier reaction. That means a Starship landing on Mars could, in theory, manufacture its own return fuel. This wasn't an accident. This was the plan from day one. Here's where the Raptor goes from impressive to almost unbelievable. The Merlin used an open cycle. Some exhaust wasted, some efficiency lost. That's acceptable conventional. The Raptor uses something called a full-flow staged combustion cycle. Let's break that down, because understanding this is understanding why the Raptor is in a class by itself. In a conventional rocket engine, you need turbopumps, incredibly powerful spinning pumps that push propellant into the combustion chamber at high pressure. To spin those pumps, you burn a little bit of your fuel in a device called a preburner. In most engines, the exhaust from that preburner gets dumped out wasted gas, wasted energy. That's the open cycle. In a staged combustion cycle, you route that exhaust back into the main combustion chamber instead of wasting it. More efficient, more pressure. Now, full-flow staged combustion means you do this for both propellants simultaneously. The Raptor has two preburners, one running fuel-rich methane, one running oxidizer-rich oxygen. Every molecule of propellant passes through a preburner before entering the main combustion chamber. Nothing is wasted. Nothing is vented. The result? Chamber pressures that exceed 300 bars, roughly 4,400 pounds per square inch. For context, a car tire runs at around 35 pounds per square inches. The Raptor runs at over 4,000. That extreme pressure translates directly into efficiency measured in rockets as specific impulse, or ISP. The higher the ISP, the more thrust you get per unit of fuel. The Raptor's specific impulse puts it among the most efficient chemical rocket engines ever fired. Only a handful of engines in history have ever attempted full-flow staged combustion. The Soviet RD-270 tried in the 1960s and never flew. Before the Raptor, no engine using this cycle had ever reached operational status. SpaceX didn't just make it work, they made it work at scale. But here's what the textbooks don't tell you. The reason no one successfully built a full-flow staged combustion engine for 60 years isn't that engineers didn't know how. It's that the system is extraordinarily difficult to keep stable. Think about what's happening inside the Raptor during a burn. You have methane and oxygen, both highly reactive, flowing through separate pre-burners at extreme temperatures and pressures. Then that pre-burned gas, already hot enough to melt most metals, enters the main combustion chamber together. Every valve, every injector, every turbopump must be synchronized to fractions of a millisecond. If one side falls behind, if the oxygen preburner gets slightly out of phase with the fuel, preburner pressure waves can build, resonating back and forth until the engine tears itself apart. Engineers call this combustion instability. And in a Raptor running at 300 bars, instability doesn't mean the engine underperforms. It means the engine detonates. SpaceX lost dozens of Raptor engines during testing at their facility in McGregor, Texas. Test stands destroyed. Engines exploded mid-test. But they treated every failure as data footage to analyze, sensors to review, models to refine. This is the brutal engineering philosophy of iterative development. You build, you test, it explodes, you learn, you build again. Faster than any agency in history had ever tried before. There's another problem nobody talks about when they discuss rocket engines. How do you stop it from melting itself? The temperatures inside a Raptor combustion chamber exceed 3,500 degrees Kelvin. That's hotter than the surface of the sun. No material on Earth can just sit inside that heat and survive. The Raptor's solution is called regenerative cooling. Before the cryogenic methane enters the preburner, it's first routed through a network of tiny channels built into the engine wall itself. It flows through the walls like blood through veins, absorbing heat, keeping the metal from reaching its melting point, then entering the combustion process, having done its first job as a coolant. It's an elegant and almost paradoxical solution. The fuel that powers the engine is also what keeps the engine from destroying itself. Combined with a compact physical design, smaller and lighter than you'd expect for an engine producing over 200 metric tons of thrust, at sea level, the Raptor achieves one of the highest thrust-to-weight ratios of any rocket engine ever built. More force, less mass, and the ability to be reused. Here's the thing you have to understand about the Raptor. Every single design choice, the methane, the full flow cycle, the extreme pressure, the regenerative cooling, the compact form, none of it was made for the sake of engineering elegance. It was made because SpaceX has a specific, concrete goal: build a reusable vehicle that can carry humans to Mars, repeatedly, affordably. The Merlin was built to survive the economics of the 2000s. The Raptor was built to survive the physics of interplanetary travel. A Starship vehicle fully stacked is powered by 33 Raptor engines in its super heavy booster and 6 more in the Starship upper stage. 39 engines, each capable of that extreme pressure and thrust, each needing to fire reliably, be recovered, and be flown again. That has never been attempted by anyone, ever. And yet the engines work. Not perfectly, not without failures. But they work well enough that the most powerful rocket ever built has already lifted off the ground and traveled farther than any previous prototype. The Raptor is extreme because the mission is extreme. Going to Mars isn't an incremental improvement over going to orbit. It requires a generational leap in propulsion technology. And SpaceX recklessly, brilliantly, dangerously appears to be making that leap. The question isn't whether the Raptor is impressive. It clearly is. The question is humanity ready for what comes next? The Raptor engine is not just a piece of hardware. It's an argument SpaceX's bet that complexity, risk, and relentless iteration can achieve something that decades of cautious aerospace engineering never did. Whether you think that's inspiring or terrifying probably says something about how you see the future. I want to know where you stand. Drop a comment right now. Is the Raptor the greatest engineering achievement of the 21st century, or is SpaceX moving too fast, risking too much? I read every single comment, and I'll be pinning the most interesting take I see. If this kind of deep dive is what you came here for, subscribe, because we're going much further down this rabbit hole. Next, we're looking at how Starship's heat shield works, and why it's just as terrifying as the engine that powers it. That video is coming soon. Stay updated. See you in the next one.